Okay, you've recorded digital audio. What does that mean? Let's look at the technical stuff. Why is digital a big deal? Well, unlike on analog tape, digital audio means you can edit it, change it, manipulate it, etc., and still have a copy of the original. You can fix errors in the rhythm of one part or the pitch in another without necessarily having to re-record everything. You can sync everything to a master clock to change the speed without changing pitch, unless you want to do both. You can create new sounds out of old ones for playback on a sampler. You can go completely out there with things like spectral synthesis or granular synthesis, using a digital sample as the basis of your manipulations. So how does it work? Well, sampling and quantizing or quantization is the best way to explain it. How that happens is that you have your microphone hooked up to an audio interface. The analog to digital converter in your interface samples the electrical signal from the microphone and reports the instantaneous amplitude of the signal every set number of times per second. This is the sample rate. How many times per second you are sampling that instantaneous amplitude. Common rates are 44.1K or 44,100 samples per second. That is CD quality. Or there's 48,000 samples per second. That is DVD quality. You also have multiples of those like 88.1 or 176.4K, which can then be downsampled to CD quality. Or you've got 96K or 192K, which can then be downsampled to 48K. These are common for pro level gear, but not really at the consumer level. Higher quality does exist, but at that point, the costs are ridiculous. So what's quantizing? Quantizing is the assigning of an amplitude value to a given sample. So every 44,100 times per second, you're getting the current amplitude value. The sample resolution is the number of amplitude values available to the analog to digital converter. This is also called the sample width, or more commonly, and what you're going to see in pretty much everything, the bit depth. So converting a signal from analog to digital is not a smooth process. Analog is continuous, unbroken, constantly changing and fluctuating, but sampling for digital systems requires us to break it up into individual discrete values that the computer can process. The sample rate tells us how many times we sample per second, and the more times per second that we sample, the smoother the resulting waveform will be and the more realistic the sound. If we sample at a really low rate, we're going to have stepped values that are going to go up like that and kind of create a pyramid type shape, but not necessarily a nice, smooth, continuous curve. As we increase the number of samples, we get a closer approximation of that curve. But there's also a limit. Digital audio cannot recreate any frequency above half of the sample rate. This is called the Nyquist frequency after the physicist Harry Nyquist, who discovered this property. So here's how it works. You take the sampling frequency and you divide it in two and you get the Nyquist frequency. So for CDs, 44,100K, the maximum frequency you can get is 22,050 hertz. Now, you'll notice that that is just above the range of human hearing, 20,000 hertz. So, can you hear everything on the CD? Yeah, probably. It's going to recreate all the sounds that a human ear can process. But if you were to go at a lower sample rate, say if your sample rate was 11,000 hertz, well, at that point, your maximum sample rate would be 5,500 hertz. Your maximum sample, sorry. So at that point, you're losing a lot of data. You're losing a lot of the high notes that would occur on a surprising number of instruments. And you're going to lose a lot of overtones. Things are going to sound muffled and kind of muted. There's just a little picture of Nyquist himself. So that ought to be enough for everybody, right? I mean, human hearing tops out under ideal conditions at 22K, but that is not correct. That added data allows for smoother digital playback and greater fidelity to the original analog signal. Some mixers will tell you that it adds more sparkle to the signal, that if you boost that 20 to 22,000 kilohertz bands, that your audio will shimmer and sparkle. But it's also essential for anti-aliasing in digital synthesis to keep it from creating foldback distortion or weird little parts where it just goes above the sample rate and you get these nasty sounds that you don't want. But mostly, if you drop down the sample rate, you can really hear the change, and it's not pretty. The lower the sample rate, the more implicit filtering is present, and the worse the resulting audio will sound. And honestly, you can always downsample when you bounce the final mix. It's really easy. So record at a high quality, at CD quality, or at a multiple of it. I usually record at 88.2. It's really not that much of a larger file size. Here's what I was talking about before. We have the analog wave, and you can see in A, we're only taking a couple of discrete sample values. So the digital result is very stepped. As we increase the number of samples in B, we get more and more definition to the original curve that can be seen. And in C, where we're sampling even more, we get an even better digital curve approximated at the result. So, quantization. We're assigning a value to each sample captured by the ADC, but what is the value? Typically, it is a binary value that will be normalized for human readability as -1 to +1. The bit depth controls the value resolution for the amplitude. Higher bit depth is better and gives you a higher dynamic range from the loudest possible sound to the softest possible sound. So if a value that's sampled doesn't hit one of the values that your system can reproduce, it rounds to the next nearest value. If you have a 16-bit sample, then you have 65,536 possible values. However, if you have 24 bits, you have 16,777,216 values. And the file size is only marginally higher. There's absolutely no reason to not use 24-bit bit depth at all times when you are recording and working with audio. It just gives you a much, much, much larger dynamic range. And here we can see quantization and how that is affected by different bit depths. In the leftmost picture, we have essentially 1 bit. It's either on or off. Then as we step up to 2 in the middle, you can see that we get more points that can be reproduced. And then at 4 in the third, we get even more definition. We get different gradients of volume that we can use when we're playing back that waveform. You can see an even bigger version of it here, where as the sample rate and bit depth increase, we get better and better waveforms from the left where it's low bit depth, low sample rate, to the middle where it's medium, and then to the right where they're both high. The higher you go on both the sample rate and a bit depth, the more accurate and close to the original analog signal your resulting waveform will be. Another thing to keep in mind is the signal to error ratio. This is the ratio of the overall signal to the sampling error. So in other words, it's the dynamic range of the system when the signal is at maximum amplitude. So there's a lot of stuff there involving math, but basically there is a 6 dB per bit sampling error that gives you the dynamic range. So for 16-bit, you have a dynamic range of about 96 decibels. At 24-bit, you have a dynamic range of 144 dB. So again, there is absolutely no reason not to use 24-bit at all time. So other reasons why you would use higher resolution: it lets you have lower noise from sampling errors or quantization rounding so that the music can be recorded at a lower volume level and accurately recreate quieter sounds. And it gives you way, way more headroom to boost the signal before it distorts when you're mixing. High def audio is technically anything beyond 48K. Like Blu-ray is 96. There's a couple of attempts at even higher rates for consumer gear like Super Audio CDs, which was 1-bit direct stream digital, or the Pono player, which was 384K, but both were miserable failures for the simple reason that above 44.1, most people honestly cannot tell the difference, and the people who say that they can are usually lying. It's a cool concept, but without incorporating surround sound like 5.1, 7.1, Atmos, ambisonics, whatever, it doesn't really sound noticeably better than a CD if you're just listening to it in stereo. So, digital file formats. This part is gonna hurt a little bit for some of you when we talk about these. There are two major categories of digital audio files. You have uncompressed and compressed. Uncompressed stores the audio in 16, 24, 32, or occasionally now 64-bit files with a defined sample rate. They can be mono, stereo, surround. Stuff like AIFF and WAVE are the most common, but there's some other rarer ones like CAF and WMA. Page 114 in the book has a really nice chart for calculating uncompressed file size for mono, stereo, etc. Compressed files operate using two different types of compression schemes. You have lossless compression, which reduces the file size without altering the original data. This is the equivalent of zipping up a file on your computer to send it to someone else through your email. The audio file is completely recoverable from the compressed file. So lots of formats do this, but the best ones are generally MP4, OGG, and FLAC. Then you have lossy compression, which removes material from the audio file using perceptual encoding. So what that means is that it masks some signals by other signals that occur at the same frequency, but at a higher amplitude. So this is basically getting rid of things that you won't hear, but that are still present in the audio track. If, for example, you have a really light brush hit on a snare drum that's getting covered up by the bass, it's going to keep the bass and it's going to get rid of the snare. Can you tell the difference? In some cases, yes, you can. And this is where it gets really painful. Yeah, you can absolutely hear the missing data. There is a massive frequency reduction. Anything over 17 kilohertz gets cut out. Sometimes, depending on how you did it with the compression, this goes as low as 15K or as low as 12K. The signals are going to sound almost like they're underwater. Now, especially if you use a low bit rate in the encoding, like when you're transferring it to MP3, you will notice some really, really bad files. The common formats for digital lossy compressed are MP3 and AAC. Supposedly, most people who are not musicians cannot tell the difference between CD quality and a 256K MP3 file, but every single musician I have ever tested this with can. The only benefit to lossy compression is the extreme file size reduction. Take a look at page 117 in the book. It will show you exactly how much data you can shave off, and it is a ton. But again, Is it appropriate for professional music? No. Is it appropriate for something that you're going to be working with and converting to other formats? Really no. Especially if you're going to do anything like spectral editing, if you're going to do any type of analysis that requires having access to all of the spectral data, or especially the higher frequencies, or if you just have a high frequency sound. Don't use lossy compression. Here's an example. On the left, you have an MP3. On the right, you have the exact same file as a waveform. You will note that pretty much everything in this case, about 19K, is completely missing, and there's a lot of stuff above 17K that is also missing. Let's talk about loops really briefly. There are a lot of different formats, but the most interchangeable are AIF or WAV files that are just properly cut to start and end exactly on bar at a specific BPM, and they usually have that BPM information in their metadata. There are specialty formats though. ACID and Apple Loops both use uncompressed files but add extra information into the metadata for loop points, transient position, stuff like that. There is SILE, or Software Information Apple Loops, which also include MIDI, synth, and channel settings all in one package. These are only accessible in GarageBand or Logic Pro. Then another really popular one is Rex, which is created in the Propellerheads Recycle program. This doesn't stretch or compress the audio, which you normally have between the transients in ACID or Apple, but instead it treats every single slice as an independent segment separated by silence, and then it maps those out over a MIDI key range. So you have a key for the first slice, then the next chromatic key is the second slice, going up by a half step you get the third, a half step to the fourth, fifth, sixth, all the way through whatever, however many you have. This is really great when you pair it with a MIDI controller, and it's become very, very popular because then you can auto map out, say, an entire loop to anywhere from 1 to 88 keys, and you get some really interesting results. Highly recommend checking that out.